Hey everyone, this is the fourth lecture. The topic is going to be multiple regression. As I mentioned before, simple regression is just when there's one variable predicting one outcome, one predictor predicting one outcome. Multiple regression is two or more variables predicting one outcome. So why do we want to use multiple regression? Well, again, it's two or more predictors in the same model. So why would we want to do that? Well, first, it allows us to control for the effects of other variables. This is really important if you think back to our second lecture about causal relationships. This gives us an opportunity to start to talk about causal relationships without an experiment. There's a lot of cases where experimentation is either not possible or unethical, and so this gives us a way to approach causality. So when we say control for, we're basically pulling the effect of those other variables out. And we're going to talk about that in more detail in a moment. It also can help clarify really strange results like what happens in Simpson's paradox, where it looks like the relationship is one way, but it's actually totally the opposite. I have a link to a YouTube video that discusses that a little bit. In other words, controlling for things allows us to understand real effects of a variable on the outcome without these other things affecting it. If you can think back to the DAGs description that we went through in lecture 2, there's always other variables that are impacting either just the outcome or the outcome and the predictor. And if you think back to the four elemental confounds, where we had the fork, the pipe, the collider, and the descendant, those help us understand what we should control for in the model, but this is actually how we do it. We use multiple regression. What's cool is we also can look at nonlinear relationships too when we're using multiple regression. So there's some things that a straight line isn't going to quite cover, and multiple regression lets us look at nonlinear relationships as well. What this does is it actually complicates the model a little bit, where instead of just a line, now we have the best fitting plane. So kind of a flat surface, or a hyperplane, which when you have three or more predictors, can't really picture a four-dimensional object. So it ends up becoming a little bit more complicated of a model. Instead of just looking at a line, now we're looking at a plane or a hyperplane in more dimensions. It can be a lot harder to visualize what the line is doing, but the regression estimates are still very interpretable, which is really nice. That's one of the reasons why we use it, is the estimates themselves are still going to be very clear. They're going to help us understand exactly what the relationship looks like. You should also know that the math behind the model is more complex. We walked through some simple versions of this before. It's going to get more complicated in this one. We're not going to require that you do the linear algebra, but we're still going to have to talk about what it's doing in very straightforward surface level terms. So some vocabulary that's helpful for really the rest of this lecture and the rest of the class is I'm going to use a lot of terms. I usually am going to stick with predictors, but there's other terms for it. Regressors, covariates, independent variables are all essentially interchangeable. Sometimes when we're talking about independent variables, we're talking about the ones of interest, the ones we really care about. And covariates are usually the ones we don't care about so much. Regardless, all of those are somewhat synonyms: regressors, predictors, covariates, and independent variables. Beta coefficients, those are the estimates for each predictor. They're the associated change in the outcome when we increase a predictor by 1 unit, holding all the other predictors or covariates constant. We'll talk about that interpretation more throughout this lecture, but I'll repeat it. It's the associated change in the outcome when we increase a predictor by 1 unit, and this is a new part, holding all the other predictors constant. And then I'm going to use the term model a lot. We've already used it a few times. A model is just a representation of y as a linear function of the predictors. In other words, it's an estimate of the linear relationship between your outcome and the one or more predictors. It's just a simplification of the world. That's all a model is trying to get at. Is we know the world is really complicated, but we want to understand the relationship between these things. A model helps us get to that by simplifying all the noise in the world and helping us try to just find what is really the relationship happening there. So in context, let's say that we want to predict the final high school GPA from several predictors, including the number of positive role models an individual had and their SES. And if you haven't seen SES before, that's socioeconomic status. It's basically how poor or rich you are in society. So maybe we're particularly interested in the association of the number of positive role models and final GPA, but we want to account for the effects of SES because we believe that is impacting both the final high school GPA and it's impacting the number of positive role models. In other words, SES is causing some part of how many role models you have and your GPA. So we can examine the multiple regression model and conclude, for example, I'll disappear for a sec. For each additional positive role model, the predictor, there is an associated 0.5 unit increase, that's your coefficient in this case, in GPA, the outcome, holding SES constant. Hopefully that highlights some of those terms, the way that we are going to be using them in this class, in the context of how we're actually going to be talking about them. Another thing that's important here is the way that we interpreted this is saying that there's some associated increase when we increase our predictor, there's some associated increase in our outcome when we hold SES constant. So what does that mean? Especially the last part, we've already talked about it a couple of times. What does holding SES constant mean? Well, it is statistically saying that we are making everyone equal on SES. And then we're saying this is what happens when everyone is equal on SES. What is the relationship between the positive role model, the predictor, and our outcome GPA? That is essentially what regression is going to do for us, is it's going to say we're going to make everyone equal on the other variables. What happens with the relationship between these two variables when we do that? Now note, in this case, we defined SES as this other predictor, but the model, when we actually use it, is going to see all the variables the same. It's just going to be positive role models, one predictor, SES is another predictor. It's when we go to interpret it that we're actually going to define which one we're holding constant and which one we're actually looking at the relationship. Another thing that's nice about regression is that multiple regression is essentially the same as simple regression in that it's going to give us predicted values. That's those y hat values. So for each person, the I, the subscript I, for each person, we're going to get a predicted value. What the model predicts would be their outcome. And then we still have, so let me go to the next, highlight this a little bit. We still have one intercept. There's still just one point that the line or the plane is going to cross the y-axis when both x's are 0. So when x1 is 0 and x2 is 0, our intercept is telling us that is our average y when both of those are 0. And then we also have these two predictors in here. And so now we're just adding, instead of just adding one predictor with one coefficient, now we're adding two. So we still have a beta coefficient. We're going to put a subscript 1 on that. And we have a predictor we're going to call x1. And you'll note that there's just one coefficient. There's no subscript I, so not everyone gets their own coefficient. There's just one for everybody. And then everyone does have their own x value. So there's x sub 1I saying that everybody has their own value for x sub 1. And then we say plus, and then we have this beta coefficient 2, which again is the same for everybody. And then we have this x2 sub I. What's great about this is the whole model. And what it tells us is we can get a predicted value for each person. We'll need to calculate the intercept. We'll need to calculate the beta coefficient for x1 and the beta coefficient for x2. How do we actually get our predicted value? Well, once we have the model, let's say we ran the model and we got an intercept of 3. We got a beta 1 coefficient of 2.5 and a beta 2 coefficient of 5. Well, it turns out we can just plug in values. So here we have a column of x1s where we have 2, 5, and 3. Those are for different people, thus the ID variable. So for person number 1, they scored a 2 on their x variable and a 0 on their x2 variable. So what we can do is actually just plug in those numbers to get our predicted value. When we plug in the 2, where the x1 is, we get 3 plus 2.5 times 2, because that's what they scored, the 2, plus 5 times 0, that's what they scored on 2, the x2 variable. When we plug that in, we get this 3 plus 2.5 times 2 plus 0, which gives us 8. We can do that same thing for the other two, where we plug in 5 and 4 and plug in 3 and 2. When we do that, we get 8, we get 35.5, and 20.5. Try to do that on your own. Make sure you understand this. This is a common thing that I put on the exams, is having you just fill in the gaps so that you can understand where the predicted value is coming from. All right, because regression, the simple regression and multiple regression are essentially the same, just multiple regression is a little more complicated, we're still going to have to work with residuals. And residuals actually work the exact same way as they did before. There's still going to be the difference between the predicted value and the observed value. So what did they really score, and what does the model predict that they would score on the outcome? And generally, when we're thinking about this, is that smaller errors or smaller residuals generally means a better model. So if we're plugging in variables, if a variable helps our model, it's going to make the predicted value better. It's going to make it closer to the observed values, which in this equation means that the sum of squares residuals will go down. This error term, this residual term, will go smaller as our variables explain more and more of the outcome, or as our predicted value gets closer and closer to the actual observed values. A note here, just an aside, for those that are interested, OLS is what's called a closed form method. That means math can solve the problem alone. So I call it the minimization, which is just because we're trying to find the line that is closest to all the dots, or the line that minimizes the residuals. And you can actually just use math to solve that. But if we really wanted to, we could solve for the best fit line by repeatedly adjusting our beta coefficients until we minimize the error. So we could just try one thing and then try another, and if that thing was better than our first one, then we would try to find something that was better than the next one, and we would just do it iteratively until we found the right line. This is a step-by-step or iterative method, and it's typically used for more complex problems. It's often used, some form of it is often used in machine learning. So for us, most of the stuff we're going to do is it's actually just going to be mathematically solvable. The computer will just plug in the values and get a result out. When we get into what are called GLMs later on in the class, there's going to be more of an iterative approach that the computer takes. It's going to say, I'm going to try this. Can I find something better? If so, then I'm going to use that one. Can I find something better? And it just moves until it finds the ideal thing. So as an example, we can look at the Parks and Rec and Office data set. And let's go back to our original example we used in last lecture. So we realized last time that awkwardness alone maybe didn't do the best job predicting income. So we think awkwardness probably does impact income, but we're probably missing some things. And if we think about our DAG, there's probably other things that impact awkwardness and impact income. Let's just say that here we're going to use a second predictor and we want to use depression. And we happen to have a really good measure of depression, so we want to control for that. In this data, we don't show the p-values or anything, but we're showing the intercept, the estimate for awkwardness, and depression. What these are called, the regression coefficients or beta coefficients for awkwardness and depression, those numbers right below it, those are called partial regression coefficients. They're partial. Whenever you see that word, it means that we're controlling for something. In this case, awkwardness, that coefficient, the negative 1.99, is controlling for depression. In other words, for each 1 unit increase in a character's awkwardness, there's an associated 1,994.50 decrease in yearly income, holding level of depression constant. In other words, if we make everyone equal on depression, awkwardness is still associated with almost a $2,000 decrease in yearly income. So if we increase awkwardness, we're going to lose money. It turns out the opposite is also true. So we can say that for a 1 unit increase in depression, there's an associated $1,185 decrease in yearly income, holding awkwardness constant. In other words, if we make everyone equal in awkwardness, what's the effect of depression? Well, it's that number. And then the intercept, that's telling us if awkwardness and depression are both 0, what is the average income? And in this case, it's negative 76,000. Doesn't really make sense. You can't really have a negative income. What that usually means is that awkwardness of 0 and depression of 0 probably aren't actually in the data and are probably not very useful numbers. So sometimes the intercept isn't going to tell us something super useful right to begin with. All right, so you might be wondering, how do we actually get the partial regression coefficients? And even if you're not wondering, I'm going to tell you, there's really two main approaches of getting the partial regression estimate. The first one is using the residuals, and if you remember, what are residuals? It's the difference between what we predict and what was actually observed for each person. And residuals are everything that's left over from the outcome of the model that could not be explained by the predictor. So what we're going to do here is we're going to go through this 4-step approach. First one is obtain the residuals of when y is predicted by all the other covariates, not your predictor of interest, not x. We're going to call those YR. They're the residuals of y after we've taken out all the information that the covariates can explain. So it's just going to leave us with part of what's left of y. And then we're going to obtain the residuals of x predicted by the covariates. So this one's weird. We're going to use our predictor as the outcome in this mini model. X is going to be predicted by all the covariates that Y was predicted by, and we're going to get the residuals of that. In other words, it's everything left in X not explained by the covariates. Thus the residuals, we'll call that XR. And then we're going to run the regression of YR predicted by XR. In other words, we have what's left over of Y that wasn't explained by the covariates already, predicted by what's left over of X that wasn't already explained by the covariates. And then this gives us a partial regression coefficient of X predicting Y when controlling for the covariates. The algebra way is a little bit more straightforward if you understand linear algebra. It is just that formula. For this class, we're not going to actually use that, but it is actually really good to see that linear algebra, once understood, actually, for the most part, simplifies this calculation. Instead of having to get the covariates, the residuals of Y predicted by the covariates, and X and all that for each one, instead, it's just one equation that we can plug in. We can also get a correlation when controlling for covariates. This is often termed a partial correlation. Some fields use this fairly often, but others don't. A partial correlation is a correlation after after getting the residuals like we did in the previous step. With that in mind, how might you interpret a partial correlation? So if you consider what we just learned about partial coefficients, this is the correlation between the two variables, income and awkwardness, when we controlled for depression. In other words, when everyone is equal on depression, what's the relationship between income and awkwardness? And here it's negative 0.66. So I've already mentioned this. We're going to do the same steps to get the partial correlation. I put it in the slide so that you can see them. But it's really the same steps. We're just doing a correlation instead of a regression. What's interesting is you actually can square the partial correlation. And when we square it, we get what's called the squared partial correlation, and that's a proportion of the variance in Y explained by X and not explained by the covariates. In other words, it's the unique amount of the variance that X accounts for in Y. How much of Y does X explain uniquely, not with the covariates? We also have standardized coefficients. This is when we standardize our outcome and our predictors. And if you remember back what standardizing means, it's just basically creating z-scores. So you have your value, you minus the mean, and you divide it by the standard deviation. When you have just z-scores, this gives you what's called a standardized regression estimate. We're going to talk about effect sizes a lot more in a later unit. But what this does is it puts the coefficient in the units of standard deviations instead of whatever units they were in before. In other words, if we're looking at the awkwardness one, we have negative 6.4 e to the negative 1, which just means 0.64. So negative 0.64 is the coefficient on awkwardness. And all that's saying is that for a 1 standard deviation increase in awkwardness, there is a negative 0.64 decrease in the income in standard deviation units. Another way of saying that is the income will go down 0.64 standard deviation units for every 1 standard deviation unit increase in awkwardness. Standardized coefficients are really useful when the raw values of your predictors and the outcome are not really interpretable things. In this case, awkwardness maybe isn't super interpretable, but the outcome is income in dollars. That's generally pretty interpretable. So this may not be an ideal place for a standardized regression estimate, but in a lot of cases for our fields, we have units like depression that we don't really intuitively understand what those units actually mean. In those cases, standardizing can be really useful. And what it tells you is for a 1 standard deviation unit increase in awkwardness, how much in standard deviation units does the outcome change? And the effect sizes are more similar to correlation effect sizes. We've already talked about this. The two important considerations are what units is a standardized effect in. It's in standard deviation units. And are they similar to partial correlations? Yes, they're not the same, but they're very similar. Some more effect size measures that we'll go into more later on. We have multiple correlation, which is just capital R, which is essentially the correlation between the predicted values and the observed values. So the better our model is, the more that we can explain about our outcome, the closer our predicted values will be to the observed values. That means if R is big, it's higher, that means our model is stronger. We also have R squared, there we go, which is the proportion of variance accounted for by the model. So all the predictors in the model, how much do they explain of the outcome? In other words, it's a proportion of the variance in Y that can be explained by all the predictors together. The can be explained by can also be stated as variance accounted for, variance attributable to, variance explained by. Those are all synonyms of can be explained by. I wanted to highlight what this looks like from a Venn diagram standpoint. I think it can be really helpful to think through. So we have three variables. We have x1, x2, and y. Y is our outcome. x1 and 2 are predictors. We can get various measures of effect here with the R squared versions. So we have R squared, which is A, B, and C all added up, divided by all of Y, which is A, B, C, and D. In other words, how much of Y does x1 and x2 explain together? So it's all of that A, B, and C together, divided by all of Y, including the stuff that the variables don't explain, which is in D. So that's your R squared. We also can get the partial R squared, which we talked about a minute ago, by doing A divided by A plus D. So when we're looking at that, we're dropping both B and C because that was explained by the other variable. We're just taking that out and we're just looking at everything that is not explained by x2. Vice versa is also true. So to get the effect, the partial R squared for x2, then we drop A and B, we take that out, and we just have what's left in C and D. So we do C divided by C plus D. And that's your partial R squared. Your R squared is everything together divided by all of Y. The partial ones take out what the other variable is explaining and just look at what's left over. So there's some important things that go along with this. When we should control for something that we don't have that variable measured. So say we want to control for experience working at this company when we're looking at awkwardness and income. But let's say in our data, we don't have that measured. We look at our DAG and we're thinking, yeah, we really should control for years of experience at this company to really understand the effect of awkwardness on income. But we just don't have it. What this is called is it's omitted variable bias. It's bias that comes from variables that are omitted, things that should be in there but aren't. turns out we can predict the overall way that this is going to affect your estimate. So for example, we have this estimate of awkwardness predicting our outcome. We may want to know, okay, we don't have years of experience measured. Do we know what kind of bias is happening to our estimate? And this table is trying to highlight what that will look like. So if your estimate itself is greater than 0, and the correlation between your measured variable, which is x1, and your unmeasured variable, which is x2, if it's positive, if those are positively related, then the B1 is overestimated. It's too high. When the correlation between x1 and x2 is negative, that means your coefficient is underestimated. It's too low. The real estimate would be higher. And then it reverses. So when your slope, your beta coefficient, your B1 is negative, it's less than 0, and the correlation between the two variables, x1 and x2, is positive, then B1 is underestimated, it's too small. And when the correlation between x1 and x2 is negative, B1 is overestimated. I'm going to have some kind of shortcuts for you to think about this. We'll talk about that more in the in-class discussion, but you can think of it as if your slope is positive and the correlation is positive, a positive times a positive is a positive. So the bias is positive. You're biased in the positive direction. It's overestimated. When your slope is positive, but the correlation between the two is negative, then your slope is underestimated. It's negatively biased. So one time positive times a negative is a negative. And you see the same thing down here. When your slope is negative times a positive, you get negative. It's underestimated. When it's negative times a negative, it's a positive. Hopefully you're able to see that a little bit. We'll talk about it more in our in-class discussions. To help you see what this really means, why there's a omitted variable bias, why things are wrong, let's consider this example where we have y is our test scores. We're going to predict that from the level of attentiveness, which is our x1, and number of hours studied, which is x2. And remember, area 1 is what x1 uniquely describes in y. 2 is what both of them together describe in y. And 3 is what x2 uniquely describes in y. So 2 is this kind of shared area where x2 and x1 both explain it, and so we can't really say it belongs to one or the other solely. Because of that, if we don't include x2 in the model, maybe because we didn't measure that variable, then we are estimating the impact of x1 on y by areas 1 and 2. We're including both of those. 2 should be thrown out because we know it has stuff to do with other variables. What this does is, for our R squared and things like that, it's an overestimation of the effect of x1 on y. But our beta coefficient, it could be overestimated or underestimated depending on the direction of the effect. What it's going to do is it's going to impact it, though. It's going to move the estimate in some way or another. We don't know how much it's going to move, but we do have an idea of what direction it is based on the table on the previous slide. Hopefully that makes some sense. Whenever we're missing something that should be included, technically we are adding impact that doesn't belong to that variable. We're giving it stuff that it doesn't actually deserve. x1 only should have 1, but we're giving it 1 and 2. To understand this a little bit more, these are some really good resources to take a look at. Some about omitted variable bias, some multiple linear regression tutorials in R. Regardless, I recommend that you take a look at these to make sure that you're understanding these concepts well enough to feel comfortable with something like an exam or the in-class discussion that we're going to have. Please reach out if you have any questions. Enjoy this comic and this beautiful landscape, and I will see you in the next lecture.